Today I want to introduce some of the most important concepts in physics, and that's the concept of energy and work. So the concept of energy is a really important concept in science and engineering, and every physical process that occurs in the universe involves energy and energy transfers or transformations. But it's not so easy to define energy. The traditional definition is energy is the measure of a system's ability to do work. But what we mean by work probably isn't what you think of when you think of your traditional definition of work, like I'm going to work or I work to get paid. It's work in the sense of being able to cause a displacement of a system through a force. So we're talking about being able to move things around. So conservation of energy is a really sort of fundamental concept in physics. It's one of the things that we hold sacrosanct, okay? Energy is conserved. What that means is that energy can't be created or destroyed. So if the total amount of energy in a system changes, that can only be because the energy was transferred out of that system and given to another system. For example, if you use gasoline to power your car, the gasoline is burned and that transfers the energy from the gasoline into the car and causes the kinetic energy of the car. So it causes the car to move along. There's all kinds of ways to transfer energy. The one that we'll talk about today is work, and that's a force that causes a displacement or motion of a system. So you can push or pull on a system, in other words, and that'll cause it to move, and that'll change its energy, and that just makes sense. So that's what we'll talk about today. But bear in mind that there's other ways to cause energy transfer in a system. You can do it via mechanical waves, like this clock radio is putting out sound, so you could put out sound, or water waves would also cause energy transfer. You could do it via heat. Okay, if you put food on top of a burner on your stove, you're going to heat it up, and that changes the internal energy of the system. You can do it by transferring matter to or from the system. So if you put gasoline in your car, you're adding energy to the system of your car. You can do it via electrical transmission. If you flow a current into the hairdryer, then energy is being transferred from the power plant to your hairdryer, which allows your hairdryer to run. And you can do it from electromagnetic radiation. For example, we get a lot of our energy from the sun. So most of our energy comes from electromagnetic radiation from the sun, and that's the ultimate source of all energy on this planet, actually. So let's focus in on work, one of the methods that you can use to transfer energy to or from a system. The definition of work, the work done by, for example, a constant force, is defined as the distance moved multiplied by the component of the force in the direction of the displacement. And so the equation that describes that is that the work is equal to the magnitude of the force times the distance of the displacement d times the cosine of the angle in between the force and that displacement. Work's a scalar quantity, okay? It's not a vector. All energy transfers and work, they all have the same units, and those units are joules. Since we know what the dimensions are for work, force times distance, then we can figure out what those units are. 1 joule, then, in SI units, has to be the unit of force, the newton, times the meter, the unit of distance. So 1 newton meter is equal to 1 joule. If you break that down even further, a newton is a mass times an acceleration, and so a newton is a kilogram meter per second squared. And if you multiply that times another meter for the displacement, then you've got kilograms meters squared per second squared for the units of joules. So sometimes I'll interchange my notation, use delta R for my displacement and D. It's all interchangeable, but it all means the displacement. So the work here is F delta R cosine theta. You measure your displacement from the point of application of the force to where the object ends up. Okay, so that's how you measure your displacement. It's also important to know that a force does no work on the object if the force doesn't move the object, if it doesn't cause a displacement. So you can push on a wall all you want, right? But if the wall doesn't move, you haven't done any work. You're going to be tired, but you haven't done any work in terms of our physics definition of work. Also, the work done by a force on a moving object is zero if the force is applied perpendicular to the displacement, okay? So if the displacement's to the right and the force is up, then that force didn't do any work to cause that displacement, and there must have been another force at play. So, for example, here to illustrate that point, here's my block, okay? And it's got three forces acting on it. It's got the normal force acting up, it's got gravity acting down, and it's got a force that's kind of acting up and to the right. And then the displacement is to the right. So the force that's acting up and to the right, that's what caused the displacement. It caused the object to move. So that force does work. But the normal force acts straight up and gravity acts straight down. And those things didn't do any work because they were perpendicular to the displacement. Another way to think of it is the angle in between those forces and the displacement is 90 degrees. And the cosine of 90 degrees is always 0. And so the equation for work tells you that that didn't do any work. Another thing to realize is that centripetal forces do no work. So, for example, the moon orbits the Earth here in a circular orbit, and it's the force of gravity in between the Earth and the moon that's causing the orbit, okay? But the displacement is always tangential to the circle, and the force is always in. So that is causing a centripetal force, and so it did no work. Now, like I said, work is an energy transfer. So if work is done on a system and the work equation for work gives you a positive number, then that means that energy is transferred to the system and the energy of the system increases. An example of that is I push on an object and that causes an acceleration and the object speeds up, okay? So its energy is increased. If the work done on the system is negative, then energy is transferred from the system and its energy decreases. For example, friction can slow down a sliding object, okay, decreasing its energy. So friction is negative work because it acts opposite to the direction of motion, okay? So if the displacement is to the right, then friction acts to the left. And the angle in between right and left is 180 degrees, and the cosine of 180 degrees is -1. So that means that friction will have negative work. So there's all kinds of problems that you're going to encounter in this chapter for work done by a constant force. So here's how you do those things. First, you should always draw your free body diagram first and foremost and choose your coordinate system. I encourage you to choose the coordinate system such that one of your axes is aligned with the direction of your displacement. That's probably easiest. Then, if there's any unknown forces that you're going to need, you might need to apply Newton's law to determine them. So you'll need to use the techniques that you used in the last chapter sometimes with the sum of the forces equations to figure out the values of any unknown forces. Then you're going to use the equations for work for each force that you have drawn on your free body diagram, and you find the work done by each specific force. And then to find the net work, you sum them up. Sum up all those works, okay? And that's the approach. So let me do an example problem for you so you can see what I mean. This example problem says a 15-kilogram block is dragged across a rough horizontal surface by a 70 Newton force that acts at 20 degrees above the horizontal. If the displacement is 5 meters and the coefficient of kinetic friction is 0.3 between the block and the surface, find the work done on the block by the 70 Newton force, the normal force, gravity, and friction. Okay. So my first step, step number 1, was to draw my free body diagram. So here I show my block in green, okay? And then I show all the forces acting on my block. So I've got my 70 Newton force, and that's going to act kind of up and to the right. If I want to, I can break that into my components at this time. My x component is going to be 70 newtons times the cosine of 20 degrees, because that's the angle that it makes with the horizontal. And the y component will be 70 newtons times the sine of 20 degrees. Now I also have my normal force, which acts straight up, gravity, mg, which acts straight down, and my force of kinetic friction, which is going to act to the left, opposing the direction of motion. Okay? Now at this point, I don't know what my normal force is. I don't know what my force of kinetic friction is. I do know gravity because it gives me the mass of the block, and I can multiply that times 9.8 meters per second squared to get gravity. But I am going to have to apply the sum of the forces equations in order to figure out what the values of my normal force and my kinetic friction is. So I do my sum of the forces in y, okay? The sum of the forces in y is going to be equal to 0 because the block's not accelerating in the y direction. And that's equal to my normal force plus the y component of my 70 Newton force, 70 newtons times sine of 20 degrees. Those both act up, so they're positive, and then subtracting minus mg for gravity. Now I can plug in and solve for my normal force, okay? Solve for that. I get my normal force is equal to gravity minus 70 newtons times the sine of 20. Gravity is 15 kilograms times 9.8 meters per second squared. When I multiply all that out and solve for my normal force, I get 123 newtons for the value of my normal force. Now I definitely need that normal force because I've got the force of kinetic friction. So to find the force of kinetic friction, I multiply my coefficient of friction times my normal force. When I do that, I get 0.3 times 123 newtons for a magnitude of my normal force of 37 newtons. Now that I've found my forces, I can calculate the work done by each force as it asked for in the question. The work done by the 70 Newton force is going to be the magnitude of the force, 70 newtons, times 5 meters, which is the displacement, times the cosine of the angle in between the force and the displacement, which is 20 degrees. And then when I multiply all that out, I get 329 joules. The work done by my normal force is 123 newtons times 5 meters times the cosine of 90 degrees, because it's a 90-degree angle between the plus x direction and the plus y direction. Since it's at a 90-degree angle, the work done by the normal force is 0. The work done by gravity is also going to be 0, because the cosine in between the cosine of the angle gives you 0 in between down and to the right. That's 90 degrees, and so cosine of 90 is 0. The work done by kinetic friction is going to be 37 newtons times 5 meters times the cosine of 180 degrees, because my displacement is to the right, but friction acts to the left, and there's 180 degrees between right and left. And so that gives me, when I multiply it all out, minus 185 joules for the work done by friction. Okay? So that gives me the work done by each of these forces. Now I want to define one of the types of energy, and that's kinetic energy. So energy can take many different forms. It can take its form of stored energy, chemical potential energy, electrical potential energy. It can take the form of the energy of motion, which is kinetic energy. So it can take a lot of different forms. But the one that we're going to talk about right now is the energy of a particle due to its motion, which is called kinetic energy. The equation that describes translational kinetic energy, which is moving back and forth, up and down, right and left, but it doesn't include rotation, so it doesn't include spinning, okay? Translational energy is translating in some direction. So that equation for kinetic energy is 1/2 mv squared, where m is the mass and v is the speed of the particle, okay? It's energy, so it's a scalar, and because it's energy, its unit is joules, just like any other form of energy. So a change in kinetic energy is one possible result if energy is transferred into or from the system. Its translational energy of motion could change. It could speed up, in other words, or it could slow down, and that would be one result of energy transfer. So we can link the work with the change in the kinetic energy on the system. Let's say that, for example, here we have this bus, and the engine of the bus and the friction between the tires of the road are causing a net force to the right on this bus. So it starts from some slow speed, v1, and at some displacement later, it's going faster, v2. Okay? That means that there was an acceleration acting, okay, on the bus. It accelerated. So this net force is equal to m times a, the acceleration, is times d, the displacement, would give us the work. Okay? Now, if we solve using our kinematics equations for the acceleration, remember that we had the kinematics equation vf squared is equal to vi squared plus 2 times the acceleration times the displacement. Okay? So if you solve for the acceleration and plug that in for a here in this equation, you get md v2 squared minus v1 squared over 2 times d. All right? So that's just using our kinematics. Now the d's cancel out, and then we end up with 1/2 mv2 squared minus 1/2 mv1 squared. Well, that's just the kinetic energy at point 2 minus the kinetic energy of the object at point 1. So this specific example actually leads us to an equation that we can apply generally. You can sum up the works done on a system, and that's going to equal to the change in the kinetic energy of that system. Okay? So if the work results in a translation of the system, a displacement, then the sum of the works will equal to the change in the kinetic energy. So if the network is positive, then the kinetic energy increases, it speeds up. And if the network is negative, the kinetic energy decreases and it slows down. That's the work kinetic energy theorem. And of course, because work and kinetic energy are both energy, forms of energy or energy transfer, they are all measured in joules. Let me do an example problem for you. This one's a little trickier, but I think it's kind of interesting. So you have a 4-kilogram block, and it's lowered down an incline a distance of 5 meters from point A up the incline to point B, which is slightly down the incline. To slow the descent, you have this horizontal force that's applied to the block between point A and point B. So the horizontal force is kind of pushing into the hill, okay, slowing the descent of the block. The kinetic energy of the block does increase, though, even though the force is trying to slow its descent. So the kinetic energy at point A is 10 joules, and at B, it's 20 joules. So how much work is done on the block by the force of friction between point A and point B? All right? So it sounds kind of tricky, but we're going to apply the same sort of ideas that we did in our previous example. So the first thing that I do is I draw my free body diagram for my block. This one's got 4 forces acting on it. Okay? It's got the normal force acting perpendicular to the incline. It's got gravity acting down. It's got that force, okay? Now, I redrew it. It was pushing on the side of the block in the previous slide, but I just moved it over so that you can see that all the forces are acting on the center of mass in the block. So the force that's slowing the descent I drew here, and it's pointing to the left. And then, acting opposing the direction of motion, I've got the force of kinetic friction acting up the ramp. Okay, so those are all there. Now I've also inserted some of the angles that you might see. It's a 37-degree incline. Now I've chosen axes that I've indicated here with dashed lines. And the axes are, the x-axis is parallel to the ramp, okay? And then the y-axis is parallel to the normal force, which is perpendicular to the ramp, okay? And those are indicated by the dashed lines. The displacement is going to be in the plus x direction down the ramp. Now, gravity, since the ramp is 37-degree incline, is going to make a 37-degree angle with my y-axis, which means that it's making a 53-degree angle with my x-axis because there's 90 degrees in between my x and my y-axis. Now also you can see here that horizontal force is making a 37-degree angle with my x-axis, okay? So it's making a 37-degree angle downward from my negative x-axis here. So that's all indicated on the drawing. Now we're going to apply that work kinetic energy theorem, which says that the sum of the works is equal to the change in the kinetic energy. Here the kinetic energy increases. It goes from 20 joules, or it goes from 10 joules to 20 joules. So delta K will be 20 joules minus 10 joules, which is equal to 10 joules. Now I've got to figure out all the works that are on this system, okay? So remember, the equation for work is the force times the displacement times the angle in between the force and the displacement. Here, for the 10 Newton force that's acting horizontal to the ramp that slows the descent, that's 10 newtons times 5 meters for the displacement times the cosine of 217 degrees. Now, how did I get that? Because the displacement is in the plus x direction. Now this angle is 37 degrees with respect to the negative x-axis. So you've got to swing from the plus x to the minus x, and that's 180 degrees, and then add 37 degrees down. So that's 217 degrees total. So the work is 10 times 5 times the cosine of 217, which gives you negative 40 joules when you multiply all that out. The work done by the normal force is going to be 0 because your normal force is perpendicular to the direction of the displacement, and so you get cosine of 90 degrees is 0. Gravity this time, it does do work though, okay? Because the displacement is down the ramp, and gravity is not perpendicular to down the ramp. It's got a component down the ramp. So we figure that out. 4 kilograms times 9.8 meters per second squared, that's the force of gravity, times the displacement, which is 5 meters, and now times the cosine of 53 degrees, because 53 degrees is the angle in between the downward force of gravity and the force down the ramp to the displacement, okay? And if you multiply all that out, it gives you the work done by gravity of 118 joules. What the problem asks you for is the work done by friction. So we don't know what that is, okay? We don't know what the work done by friction is. And in fact, we don't even really need to solve for it here because I've got the works done by all the other forces and I know what the change in the kinetic energy is. So I can do a little shortcut. I'm going to sum my works and set it equal to the change in kinetic energy, which is 10 joules. So all the other works are minus 40 plus 0 plus 118 plus my unknown work done by friction, which I'm going to solve for, and that equals 10. So now I've got one equation and one unknown, and I can solve for the work done by friction, which gives me negative 68 joules. The negative sign makes sense because friction acts anti-parallel to your displacement. It acts up the ramp, and your displacement is downward. And so it will work to slow the block, suck energy out of the system. So that's a negative work. Okay, we'll do a lot more examples with work and kinetic energy in class, and I'll see you there.